hard stuff coming up in our last couple weeks of class. We really need to get a jump on parameterizing surfaces so that Tuesday before Thanksgiving isn't too crammed. We want to take our time with, we're going to do surface integrals on Tuesday before Thanksgiving. So we need a little extra time here for parameterizing surfaces. So here's what this is about. So remember that we did this with curves. We parameterized curves, and that took a single parameter, which we usually said was t, and that was possible to do with one parameter, even when the curve was in R3, because curves really are one-dimensional things. Even if they move through higher dimensions, at a given point you can only go one direction, and there's positive and negative. So that's a one-dimensional set of points, a curve. So surfaces then are those are two-dimensional graphs. Even in R3, they're still two-dimensional. We can use two parameters. So for many, there's just still two ways to go from any point. So therefore, it's possible to parameterize a surface with two parameters. So generically, u and v, but we'll use variables that are appropriate in every given situation. But u and v is kind of a generic choice for parameterizing surfaces with two parameters, like t is the generic choice for one parameter. Okay, so let's do some examples. The first type of example is surfaces that are given as z equals f of xy. And these are maybe the easiest ones because we can just use x and y as the two parameters, and then z is defined as a surface. So here's some examples. So f of xy, so we can write our vector function, right? So of x and y, in this case, x and y. And so we have to write, so this is in R3, we have to write the three coordinates, x, y, and z, using two parameters. And like I said, when you have z as a function of x and y, the natural choice here is use x and y as the parameters. So x is just x, y is just y. So that's a parameterization of a surface in R3. Surfaces in R3, we're still dealing with a three vector, right? A vector with an x component, a y component, and a z component. It's just that we have to write all three of those components in two variables. So this does it for this one. Okay. Similarly, if we're going to write the part of this plane inside the unit square in the first quadrant of the xy plane. Okay, so again, planes then can be rewritten as z as a function of x and y. So we could do 2z. Z would be 4 minus 5 halves x plus 3 halves y. And once again, we have z as a function of x and y. So we could parameterize this plane using parameters x and y. Again, these parameterizations will have three components, an x component, y. So this is still x, y, and z, written as a vector, an R3 vector. Okay, but now it said only for the xy ordered pairs inside the unit square in the first quadrant of the xy plane. So the unit square is from 0 to 1, 0 to 1. So just inside the square then, we'd have to qualify. It doesn't change the definition of the points, it just restricts them. So then we'd have to include with this the restriction that x is strictly between 0 and 1, and y. So that would be defining all the points described here on the plane for the xy points in the unit square. Okay, last, the top half of the cone, z squared equals x plus y, 1 squared plus y squared below z equals 7. So, so the top half of the cone would be when z equals, so when z equals plus or minus the square root of all this. So the top half would be the positive. And so we can, again, use this really simple parameterization where x and y are parameters. And then we would say below z equals 7, so you might think z is less than 7, but that's, you can't really do that because z is not one of our parameters, right? So the restrictions on the surface, like a boundary bounding the surface, that has to be expressed in terms of our two parameters. So this could be at most 7. So we could say, and if we wanted, we know that that cone doesn't go any lower than 0. So if we wanted, we could say that. And so that would just give the part of the cone that we want expressed in the two variables that are parameters for this function. So let's next look at cylinders. So for cylinders, we know that cylinders have a missing variable, and then the other two variables form a curve which is extended along the axis of the missing variable. Remember, that was our definition of cylinders. So let's try this example. So the part of y equals e to the minus x, something like that. And so then parameterizing that, we'd have, what are we going to use then? So again, when we think about this, we're thinking about we need to write all the points on this surface using two variables. So what two variables are going to allow us to do that? Well, if y is e to the minus x, then we want to use x as one of them, because then y is e to the minus x. So parameterize the curve, the cross-sectional curve, we just use one parameter. And then since z can just run freely this way, we just take that curve and extend it freely in z, then that'll be our other variable, it'll just be z. Okay, and then we want above z equals 2, so that's something. Okay, so that's how cylinders work. Use one of the parameters for the curve, the cross-section curve. The other parameter is just going to be that variable for which the curve runs parallel to its axis. Now, lots of these surfaces are circular in nature, and often it's most advantageous to use polar variables for these. All right, so let's look at the paraboloid x equals y squared plus z squared. 5. So what two variables do we want to parameterize this paraboloid? So start with y and z. Because x is a function of y and z, so we could write it as y squared plus z squared, and then y and z, and that would be valid. But if we wanted to do this in polar coordinates, so now the polar coordinates, now we're talking about the polar plane being the yz plane, not the xy plane. So then our angle theta would be swept this way in the yz plane. And then the radius would be the distance from the x-axis, not the z-axis. So radius would be like this. Okay? R theta. So what would y be? Y would be r cosine theta. Just like, it would just be like x in the xy plane for the polar plane. And then z would be our sine theta. And when we do y squared plus z squared, what are we going to get? Y squared plus z squared is going to equal r squared. Because cosine squared plus sine, you can factor out the r squared, cosine squared plus sine squared equals 1. And then we need from x equals 0 to x equals 25. So when x equals 25, it's r squared, r equals 5. So we can't say x from 0 to 25 because x isn't one of our parameters, but we can say what r from 0 to 5. Okay, what about this? The part of the circular cylinder that lies in the first octant. So let's sketch that circular cylinder. Okay, and has a radius of what? Square root of 12. Now, what are going to be, so now this is a cylinder, it's circular, so we got to think about what two parameters are going to be able to define this cylinder, right? Is r one of the parameters, We don't want r as one of the parameters because r is a constant. R is constant 12. Remember, our parameters are the variables. What needs to vary? Like in this one, r varies and theta varies, right? And so then we write the x component, the y component, and the z component in terms of r and theta. Okay, so what varies here? Well, it's a cylinder, so one thing that varies for sure is this way, along the cylinder, y. So we're going to use y. So that's just going to be our y coordinate. So then we have one variable left for any y value, say this y value right here. We have one variable left to get us all the points at that y value around this circle. So what varies is going to get us around the circle? You should be thinking theta, right? You should be thinking the angle theta will get us around that circle, and the radius is square root of 12. So looking at the xz plane, then x is this way, so x is going to be our cosine theta. It's going to be radical 12 cosine theta. And then the the z component, our vertical component, is going to be the radical 12 sine theta. So you got to really be in this mindset. So it's not quite polar, but it's using that idea, using the theta. You really got to be in the mindset of what needs to be what. I got two variables to get every point on the surface. So I want a variable that gives me all these circular cross sections. That's y. And once I have a circular cross section, then what's going to get me all the points on that circle? Well, theta going around that constant r of square root of 12. And then we wanted it that lies in the first octant. So I just want starting here and then extending on this way. Like that. So how do we restrict this? How will y have to be restricted? You should be thinking y is greater than 0. And then how will theta have to be restricted? Well, from here to here would be 0 to pi over 2. And that would give us the part of that surface that lies in the first octant. Okay, how about the unit disk in the plane z equals 6? I'm going to erase here, make some room. So the unit disk is not a circle, it's actually a filled in circle. So at z equals 6, stays there. And so we want the unit disk in the plane z equals 6. And we need two variables that are going to get us the x component, y component, and z component of all these points. So we got to think about the surface as a collection of points. We need the x, y, and z of each point. We've got two parameters to do it. So right away we see that what's true about all those points. All those points have a z coordinate of 6. So we just write that down. So we got two variables left, and now I've got to get this filled in circle. Right? So you should be thinking theta. But now we need r to vary because r could be 0 all the way out to the edge of the disk. Right? So we need r to be a variable now. Here r was not a variable because the cylinder always, every point on the cylinder had a radius of radical 12. But here, on the disk, I need all points starting at the origin all along the way out to the edge of that thing. And then, so with theta and r, I can define every point in that disk. So the x coordinate of those points is going to be r cosine theta, and the y coordinate is going to be r sine theta, standard formulas for x and y, but all at the height z equals 6, so we're using r and theta. And what we need just the unit disk. So if r is not restricted, we get the whole plane z equals 6. So r then needs to be, the unit disk needs to be less than 1. And if we want to include this, the unit disk including its boundary, then we do r is less than or equal to 1, say. And now we've just restricted it to all points with a radius less than or equal to 1, which is inside the disk. Again, we're writing three components, x, y, and z. using two parameters. So that's going to differ from problem to problem. So you have to keep that mindset. What two variables, what two variables, if I vary them, can get me every point on my surface. Okay, we're almost done. Last is spheres. So for spheres, spherical coordinates can be used to parameterize any part of a sphere or a whole sphere at the origin. Rectangular coordinates can be used, but with one vector function of rectangular coordinates, you can get at most a half sphere, right? Because when you solve for z, you get and do the square root, you get like say plus or minus. So you're getting two halves of the sphere. So if you need a whole sphere, you'd require two functions in rectangular coordinates. So let's do the half sphere of radius 9, centered at the origin. Come together here. Okay, there we go. So we got the half sphere radius 9 centered at the origin to the left of the xz plane. And so if we did this in rectangular coordinates, we know that the equation of that sphere is x squared plus y squared plus z squared equals 81. So if we want it to the left of the xz plane, that's y is negative. So we want to solve this for y. Plus or minus, right? Plus or minus the square root of 81 minus x squared minus z squared. Left half means minus. So in rectangular coordinates then, what would our two parameters be? You should be thinking x and z. So that would be in rectangular coordinates. And we could say y is less than 0, but actually this kind of takes care of it. If we did every single point that followed this, we would get that half sphere. But we could, if we wanted to just say y is less than 0, that'd be okay. But in this case it's unnecessary because graphing every point that has these three components would be exactly that half sphere. Okay, so now in spherical coordinates, what two parameters do we want to use, right? So our spherical coordinates are rho, phi, and theta. Which two are we going to pick? Varying which two will get us every point on there. So you should be thinking for every point on the sphere, one of these is a constant, so we don't want to use that as a parameter. And you should be thinking that that's rho. Rho is equal to 9, always. So it's not going to be a parameter because our parameters are what varies to generate all the points on the surface. So we're going to have rho r of phi and theta to do this in spherical coordinates. So our x-coordinate is, we know that's r cosine theta. And r, remember, is, what is r? R is rho sine phi. So we're going to have rho sine phi cosine theta. And then we're going to write this in terms of our x and our z. And what is z? Z is simply rho cosine phi. So then our y coordinate would be just y is r sine theta. And our r is rho sine phi. So spheres centered at the origin will always have this as the parameterization, phi and theta, and then the x-coordinate being this, the y-coordinate being this, and z being this that we've derived before. But we know that our for a given sphere, rho is constant. In this case, rho is 9. So rho is not one of our parameters. It's fixed at 9. And so for the sphere of radius 9, we're going to have 9 sine phi cosine theta is our x-coordinate, 9 sine phi sine theta, and 9 cosine phi. Those are all formulas that we derived before when learning spherical coordinates. So we can write spheres now using parameterizing spheres using phi and theta. Again, this is the x, y, and z component. Now we need to get the left half of it. Right? So we just need to know, how does phi vary? Phi is going to vary from 0 straight up all the way down to pi. So we're going to get all the values of phi. And what is theta going to do? We know theta is the xy angle, right? So this is theta equals 0, pi over 2, so it's going to be pi to 2 pi. This is quadrants 3 and 4, right? Quadrants 3 and 4 in the xy plane is pi. So that would be our parameterization using spherical coordinates. And this one here would be our parameterization using rectangular coordinates. Both are valid. So you have the front page of the next written homework is all kinds of examples like all these that I've done. And when we get to the hard vector calculus, knowing how to parameterize these surfaces quickly at the start of a problem is going to really save you a lot of time. And we don't want to get bogged down in this kind of the easy step of these hard surface integrals and higher dimension integrals that we're going to be doing in vector calculus in the last couple weeks. Okay, so I hope the video helps.